In trigonometry, we look at right triangles, and I explained in the previous video that these trig functions are dynamic, they change, and I explained that sine of x is the opposite over the hypotenuse, and cosine of x was the adjacent over hypotenuse, and I want to explain how if we change the angle, how those also change. So the angle right here, this is a perfectly nice and neat 45-degree angle, 45, 45, 90 triangle. If we make all these are equal, A is equal to B, but not equal to H. A squared plus B squared is equal to H squared. This is always true for a right triangle. Now, when we increase the angle length, let's see, we make that larger. This gets larger too. I mean, the hypotenuse stays the same as 1, but the A value is going to grow and B is going to shrink. And this keeps going until the hypotenuse and the opposite side are equal to each other. And that's how it oscillates from 0 to 1. Similarly, if we were to shrink the leg, or the angle, actually, my mistake. If we were to shrink this angle, let's say we go out right here now, this is still 1, but when we drop it down, now this opposite leg is shrinking and the adjacent grows. And that's how the cosine goes from 0 to 1, because eventually this will get, shorter and shorter, and this will get longer and longer until they are the same leg, they're the same line. We can now draw another plot. We can say, like parametrically, x is equal to cosine of t, and y is equal to sine of t. A unit circle is x squared plus y squared is equal to 1. Unit meaning that it's only a length of 1. So when we plug these equations into this, we get cosine squared of t plus sine squared of t is equal to 1. And that's true, and that's based on the Pythagorean theorem with the a squared plus b squared is equal to 1. So if I were to plot this, graphing this anywhere outside of the plot is going to be equal to 1. Anywhere is equal to 1. And we now have values that are positive and negative for the different trig functions. When the x values are negative in this area, the cosine values will be negative, and when we are below the x-axis, the y values are negative, and the sine of x is negative in these region. Simply, we can say, okay, well, A, S, T, C. This is the region where the graphs are positive. This is all the regions. This is sine. This is tangent, because a negative divided by a negative is positive. And this is cosine. One easy way to remember this When I was a kid, I learned all students take calculus. That's an easy way to remember which region this is positive or negative. Just erase that real quick. All students take calculus. All students should take calculus. It's not that hard. You can do it. I kind of messed up my line. Anywhere on this unit circle is a distance of 1 away. So if we were to draw a line, say that, oh, that's really thick. Let's go a little thinner. If we were to draw, say, to right here, that's going to be a distance of 1. This is going to be a distance of 1. This is going to be a distance of 1. But what we can do, how does this make how does the trig functions matter here? Well, we can actually drop this down, and now we have a right triangle, and we can say that's angle x, and then we have, you know, sines and cosines and all the very beautiful trig functions. If we go below, we can say, oh, well, we can connect the line there, or, you know, we can drop the line down there. There's many ways to draw the triangles within the unit circle, and, you know, the x value is going to be the cosine value, and the y value is going to be the sine. Studying this unit circle takes trig functions into continuous functions that oscillate and allow for values that go beyond just 0 to 90 degrees. And it also expands beyond just 0 to 1. Now we're getting 0 to 1, back to 0, to negative 1, back to 0, sort of things. Periodic functions, like trig functions, they show up in a lot of different fields, especially in the sciences. Everything can pretty much be approximated to, say, like a triangle. For instance, if I have just looking at things, like if I'm you know, right here, and I want to, you know, look at object A, and I'm looking at object B, there's this angle in between. We can call that theta. I can also, you know, connect them. I can connect them, and I still have a triangle, but I can draw a line down to the middle. Let's imagine that this is the middle somehow. Now I have two right triangles, and this angle would become theta over 2, and I'm at position x. That's not the angle. An easy way to understand an application of trig functions would be Snell's law. This is in the field of optics. Waves have this wonderful property of changing both their speed and direction when going through a new medium. And Snell's law basically is for light going through a different medium, say glass or water or even air. Let's say I have a light and I'm shining it at this angle. We can draw, would be like the perpendicular. This would be the angle. Let's call it, let's just call it x1. And then when it comes out this other medium, let's say this is n1, This is n2. And when it comes out the other medium, it's going to change speed and direction somehow. So now let's call this x2. Snell's law says that n1 sine of x1 is equal to n2 sine of x2. And the n1 and n2, these are the index of refraction or refractive indices. This refractive index has its own value. It is defined as how fast the speed of light, c, divided by how fast it's moving through the medium. It's going to be bigger than 1 usually. It always is bigger than 1 because unless it's in vacuum, it's going to be 1. So for air, it is very nearly 1, but it's not 1. It depends on the wavelength of light. There are many different wavelengths of light. But for water, it's usually 1.33, but it depends on what's in the water, what wavelength of light we're talking about. But it usually averages around to 1.33. Now, for this specific example, I'm going to erase some things. I'll be right back. Let's say we shine light from inside the water out. So just like the example shows, let's see, we're going like this way and it's going out. It's going out this way. Let's say we're shining it at x1 is 45 degrees. So n1 is 1.33 times sine of 45. Oops, not sine of 4. Is equal to n2 sine of x2. And we want to know at what angle it comes out at. N2, let's just say it's 1. It's not, well, unless it's vacuum, but realistically, if we're inside of a pool or the ocean, it's not vacuum, but it's close enough to 1. The refractive index of air is roughly 1.0003. 1.0003. That's close enough to 1. But we could be more precise, I guess. In the previous video, I covered what sine of 45 is. It was root 2 over 2. So 1.33 root 2 over 2 we can write this as and when we find out what this value is, it's approximately 0.94. And now to find x, we take the inverse function, which I did not cover, but it would be, in this case, arc sine of 0.94, and that's roughly 1.22 radians, or 70 degrees. Going back to this, 70 degrees, if that's 45, let's change colors. If this is 45, we're going to add a little bit, so it'd be coming out like a little like that, something like that, maybe close to the third one, whatever 70 degrees is. But it goes from 45 to 70 degrees because of how the light interacts with the water. The light would, in a way, bend due to the water, how fast it goes through and travels through the water. This is just a little sample of trigonometry. I want to thank you for watching and have a good night.